Hey everyone, thank you for joining me. My name is Christian Delusha. I'm a professor in the Department of Clinical and School Psychology at Nova Southeastern University. And welcome to my video series on topics in statistics and research methods. And today I'm going to be talking about the Pearson product moment correlation coefficient, which summarizes the linear association between two continuous variables. Some learning objectives for today's videos. By the end of the video, you'll learn how to generate a correlation analysis using SPSS software. You'll learn how to interpret visual displays of correlations, how to interpret correlation matrices that you might find in SPSS output from other software programs, or articles that you're reading in the published literature. And at the end, I'm also going to show you how to compute correlations by hand using a formula based on z-scores. So let's take a look at some visual displays. Actually, first, let me orient you to the variables we'll be working with today. In these videos, I use a mixture of simulated data files and real-world data files. Today, we're going to be looking at some variables from a data file that I collected several years back at a substance use treatment center in the southeastern United States. Our correlations are going to involve three variables: anxiety symptoms, which is taken from a measure of generalized anxiety; trauma symptoms, which comes from the PCL; and self-esteem, which comes from the Rosenberg measure, I believe. Okay, now we might assume a priori that anxiety and trauma symptoms will be positively correlated with one another. And also we might assume that each of the mental health indicators will be negatively correlated with self-esteem, suggesting individuals with higher levels of anxiety will report lower levels of self-esteem. Okay, to the visual displays. So here's a scatter plot of anxiety and trauma. I put anxiety on the x-axis and trauma on the y-axis, and there's a scattering of points in the field, and that's why these plots are called scatter plots. And I put the best fit line. This plot is just from SPSS. I asked for SPSS to put the best fit line in there, and we can see that the correlation between these two variables is 0.55, and if we square that value, we get 0.30. Okay, this association is positive in nature, which in general suggests that lower values of X are associated with lower values of Y, and also higher values of X are associated with higher values of Y. Okay, in this scatter plot, we're looking at the correlation between trauma on the x-axis and self-esteem on the y-axis. The correlation is negative 0.32, and its square is 0.10. Okay, now in negative associations, low values of one of the variables are associated with higher values on the remaining variable, and vice versa. So in the figure, we see that lower scores on trauma are associated with higher self-esteem scores. And then as we move to the right on the x-axis and we go up in trauma symptoms, we're coming down in self-esteem. Okay, so low trauma associated with high self-esteem, high trauma associated with lower self-esteem. Okay, and that's the sort of defining feature of a negative association between two variables. Okay, now I'm going to shift from the PowerPoint environment to SPSS to show you how to run correlations in SPSS. So so this data file has 5 variables associated with it: ID, RAM14, anxiety, trauma, self-esteem. Anxiety, trauma, and self-esteem are the variables that are of most interest in today's video. So I'm going to go to Analyze, Correlate, and then I have a few different options there. I'm going to select Bivariate. Okay, and then I'm going to highlight the 3 variables that we want to look at. I'm going to move them into the variables box. And then these defaults are appropriate for the present context. So it's SPSS is going to generate the Pearson correlation coefficient. It's going to use a two-tailed significance test. We can actually use a one-tailed test because we have a priori hypotheses about the direction of association between the variables in question. But I'm going to leave the two-tailed default option there just for teaching purposes. And then down here, I'm going to leave the box checked for flag significant correlations. If we wanted to, we could check this box and SPSS would show only the lower triangle, and we could also uncheck the box that says show entries on the main diagonal. But I want all of those entries because I want to make a couple points about them when we look at the correlation matrix. So I'm just going to click OK here, and SPSS will run the analysis and put the output in an output window. So we're looking at the 3x3 correlation matrix that SPSS generated for us. I'm going to move back to PowerPoint because it's a little easier to sort of talk through the output in PowerPoint. Okay, so here's the 3x3 matrix that SPSS printed for us. I highlighted the entries in the cells relevant to the correlation between anxiety and trauma. Okay, so those entries are in the red box on this slide. The top entry, 0.546, is the correlation between the two variables. Underneath that, we have the significance value, which is less than 0.001, just suggesting that the significance value is a number smaller than that. And the N, or sample size contributing to this correlation, is 200. And that just means that we have 200 observations on the data file who have a valid observation on both of the variables and contributed to the analysis. Okay, on the next couple slides, I'm going to teach you how to sort of break down a correlation matrix. Students sometimes, especially when they're first learning about correlations, they sometimes get very confused with the information present in the matrix. So let's take a closer look at that. Correlation matrices are said to be square symmetric matrices. Okay, you could think of them as being composed of three elements. We've got the main diagonal in this schematic. We've got ones on the main diagonal, and then we've got a lower triangle which has a green, the entries have a green triangle around it, and an upper triangle where the entries have a blue triangle around it. Okay. Now, on this slide, I show that the lower and upper triangles are mirror images of one another. So every element present in one of the triangles has an identical corresponding element in the other triangle. And so I use color coordination here to show you which elements are redundant based on this simple 3x3 matrix. Okay, at the top of the slide here, I show you, I retain the color coordination and I put the numbers back in. So here we've got ones on the main diagonal, and then we've got the three unique pairwise correlations in the lower triangle, and then we could see the redundant entries in the upper triangle via color coordination. Okay, at the bottom of the slide, I present a less cluttered matrix, what you'll typically see in a published manuscript. Authors will either put ones on the main diagonal to suggest that the correlation of a variable with itself is 1.0. They might leave the main diagonal blank, or they might put dashes there to just say that they're not going to put the ones there. And then authors will typically give you the entries in either the lower or the upper triangle, but not both. In this case, I put the entries in the lower triangle, and then there's a table note there saying that all correlations are statistically significant with p less than 0.001. Okay. In terms of interpreting correlations, we've got three things we want to keep in mind. First is status with respect to statistical significance. Is the correlation we're looking at statistically significant or non-significant? The second element is direction of association, whether it's a positive or a negative association. And then the third element is the strength or magnitude of association. Okay. And we might also be interested in confidence interval around the point estimate. And I'm not going to talk about confidence intervals in today's video, but confidence intervals are often very meaningful and provide the user with additional information that can be of value. Okay. All right, so on the next couple slides, I want to take a short digression to talk about strength or magnitude. I say here, in theory, Pearson correlations range from -1 to +1. I say in theory because there are sometimes practical constraints with the real world data we might be working with that might make it so that the observed correlation will never reach a value of -1 or +1, but that's more of a technical point. Okay, correlation of 0 suggests that there's no association between the two variables. A correlation of 1 suggests a perfect association between the two variables. And the square of the correlation, or R square, is often used to assess strength or magnitude, and it's interpreted as the proportion of shared variance between the two variables. And R square of 0.50 suggests that the two variables are sharing about 50% of overlapping variance, and R square of 0.05 would suggest that the two variables are sharing about 5% of overlapping variance. Okay, here are general magnitude heuristics commonly used in the social sciences. Many of these magnitude heuristics derive from some of Jack Cohen's work on statistical power and effect size estimates. I have a caveat here that these are heuristics, not laws, so use them accordingly. So small correlations are around 0.10, moderate correlations are around 0.3, large correlations are around 0.5. Okay, so the squares associated with these values would be 0.01 for small, 0.09 for moderate, and 0.25 for large. Okay, students often ask when they're learning about correlations and other kinds of statistical procedures, they often want some direction in terms of how to write up the results. And so I've got a statement here in the second bullet point that you might see in a manuscript. As hypothesized, the correlation between anxiety and trauma was statistically significant and large in magnitude. And then we've got some technical statistical information. R equals 0.546, P less than 0.001. Individuals who reported higher levels of anxiety also reported higher levels of trauma. That last statement is a sort of a substantive statement that helps the reader understand what a positive association in this particular context means. Oftentimes, the variables that you're working with lend themselves, when you see a positive or a negative correlation, it's not very hard to infer what that means about the association. But sometimes variables might be coded in a funny way or a way that's not intuitive. So I always recommend giving the reader a sense, if you have space in the manuscript or the project, to give the reader a sense of the substantive interpretation so they don't necessarily have to make an inference and worst case scenario, make the wrong inference. Okay. So on the next several slides, I'm going to show you how to compute a correlation by hand. I put by hand in quotes because I'm actually going to use Excel to do the math, but the math is easy enough to do with paper and pencil if you've got a finite number of scores. So what I did was I took the data file that I analyzed earlier in the slides, and I randomly selected 14 individuals from the data file, and then I'm going to use the data from those individuals to show you how to compute the correlation by hand. So rather than stepping through the computations for 200 plus observations, we're just going to have to do it for the 14 individuals that I randomly selected. Okay, if you open up an intro stats text, you might see lots of different formulas for a Pearson product moment correlation coefficient. I present probably my favorite formula on this slide. It's called the product of the z-scores. In the numerator, we've got the sum of the z-score products. In the denominator, we've got n-1, or degrees of freedom, where n is sample size. And then I give the computations. For those of you less familiar with z-scores or standardized scores, I give the computations for zx and zy at the bottom of the slide. If we wanted to compute a Z on an X variable for an individual on the data file. In the present scenario, I arbitrarily chose trauma um, as my X variable and anxiety as my Y variable. So if we wanted to compute a Z-score for a person on the data file for the trauma or X variable, we would just take that person's score, we would subtract away the mean um, on trauma, and then we would divide that difference by the standard deviation. And the resulting quantity would be that individual Z-score on trauma. Okay. Um, so here, this just reminds us that in this case, we're going to use trauma as the X variable and anxiety as the Y variable. When we're looking at correlations, the variables are on an equal footing. So correlations don't necessarily invoke the concept of causal priority, right? Which is why I said that I arbitrarily labeled trauma X and anxiety Y. I could have just as easily flipped those around and put anxiety as our X variable and trauma as our Y variable. Okay. On this slide, I have two worksheets from an Excel file that you can download from my website. On the left-hand side there, we step through the computations for generating the Z-scores for the X or trauma variable, right? So in the B column, we've got all 14 individuals' trauma scores. In the C column, we just put the mean from the 14 observations. In the D column, we put the standard deviation. And then in the E column, we have the Z-scores for each individual. So we took the individual score in the B column, we subtracted away the mean from the C column, and then we got that difference and we divided it by the standard deviation, which is the number in the D column. And so for our first participant there in row number 2, their Z-score on the trauma variable is negative 0.889. Okay. On the right-hand side, I stepped through a parallel set of computations for the anxiety variable, which is labeled Y in the worksheet. Okay. On this next Excel worksheet, I brought in the ZX variable, the ZY variable. They're in the A and B columns respectively. And then in the C column, I generated the product of the Z-scores. And so for our first person there in row number 2, the product of their Z-scores is negative 0.195. Okay. And then toward the bottom of column C, I've got the sum of the products, which just sums over the numerical entries in the C column. I've got n minus 1, which is degrees of freedom in this case. 14 minus 1 gives us 13. And then if we form a ratio between the sum of the Z-score products and n minus 1, we end up with our correlation coefficient of 0.463. Okay, so I've got a website that is meant to be a companion to the YouTube channel and my YouTube videos. You can visit me at deluciastats.com. And if you look for the correlation video, you'll see the SPSS data file that you could download, an SPSS syntax file that will generate the output that I've presented in the slide set. And you'll also see the Excel file where I did the computations for the correlation, quote unquote, by hand. Okay. In terms of additional resources, a lot of textbooks have a chapter, general overview texts have a chapter on correlation that you could look at. Here, I really like this text by Sky Huck. It's a text that is a little bit more conceptual in nature, a little less mathematical, but he discusses lots of really great issues with statistics commonly used in the social sciences. He takes excerpts from published articles that show you how people tend to talk about, in this case, bivariate correlations, or he might give an excerpt and say, okay, this excerpt can be interpreted in a misleading way for these reasons, so don't do this, do that. So anyway, it's a nice resource to do some additional reading on correlations. So anyway, I hope you learned something from the video. Check out some of my other videos. Check out my website, and I'll see you in another video, hopefully. Take care.